IBM PNG GS. Okay. Okay. So they are the returns, right? Okay. -1. Okay, instead of this, I prefer. So what is this IFM EX, PGEX, GSEX? What is that? What are they?
The excess return.
Oh, excess return over, right? Over. So it is risk-free rate.
Yep.
Okay, market. Good. So first, beta.
I tried to make the equation to that the three sector excess returns are binded into matrix form, but yeah, I failed.
Okay, so basically I have to stack the data. So market, SML, HTML. Okay, that's fine. Okay, next what I wanna do is, okay, there is much better way to do this work, but let me use inefficient but easy to understand. Let me use method which is inefficient but at least easy to understand. Okay? So, okay. And no, it's maybe D1, D2.
SME.
Right. It's SMP. It should be SMP actually.
Oh,
Small minus big. No? Yeah. Small minus big. Small minus big. So this is PNG EX. And then D3 with GS. Goldman Sachs, right? GS. Then B. Okay. And then so let me run program up to this point. Okay, no problem. Now, okay, let me start the data together through row, okay? So I have to do R bind. So D4 is kind of now R bind. So instead of stacking the data by column, I want to stack the data by row, okay? So D1, D2, D3, okay? And what is T? T74, okay? So in that way, okay? So D4 becomes like this. So still we have only 4 columns. So first one is excess return of the stock. Second, third, fourth columns are factor returns. Okay? And instead of 74, because I stacked 3, so 74 multiplied by 3, so 7, no, why it is 719? It should be strange. It should be like this. And why? What is going on? Okay. T1, T2, T3. Very weird. Okay, which is right. Okay. Then this is right. No. Oh, sorry. T is. Oh, T is 74. But okay. This is drop the last one. Sorry, but this is right. Okay. So basically, I stack the data. So next, I have to add dummy variables. So I wanna add dummy variables for. First, let me add a dummy variable for everyone. Okay. C bind. So let's put ID for this one. So try this one. Okay, then it add 1 to everywhere. Now add 2, add 3. It is for ID of the, basically 1, 2, 3 are ID of the IBM, P&G, and GS. Okay. If I do it again, T4 looks like this. So 2, 1, 9, and 5, which is correct. So to add the dummy variable, dummy one. So DOM. So basically IBM IB DOM. IB DOM. Okay. IB DOM is I need two dummy, so I'll write one 10 20 So how to create dummy, okay? IB is 1, 2 dimension of D4 1. Okay, if I do this, so 2, okay, this is correct, and then multiplied by 0, okay? And then actually, instead of creating 3 dummies, because we need only 2 dummies, I will create 2 dummies only. Okay, so PG dummy and then GS dummy, which is basically I copy PG dum. Okay. Next. So now for one, two, actually let me create another event. So T1, no, actually N equals total number of observations. So T4, first one, and this is N. N. If one, two, three, four. Okay, so it is fourth column equals to 2. Okay, then PG dom equal should be 1. Okay, so I'm creating dummy, and then if D4 4, if that is Goldman Sachs, which is 3, then again, then I put GS dom equals 1. Okay. Okay. Let me try this. Error. Unexpected. Where's the error? again. Okay, so let me see PG done. Looks like not correct. But there is no one. Okay. I should be if D4. 1, 2, 3, 4, 5. Ah, man. 1, 2, 3, 4, 5. Okay. Not 4, it should be 5. So because I have information about the form at the fifth column, right? So the fifth column is 2, which means if it is a PNG, then I put 1 to PNG only. Okay? So let me do it again. Okay. Okay. Now let me create the data. So now D5. Okay? D5 is now C bind over D4, and then PG done, and then GS done. Okay, but in the D4, actually I don't need this fifth identifying number, so therefore column 1, 4. Okay, so I want to drop the fifth column. Okay, because it's not necessary. I don't need this anymore. So D5, something like that. So let me check D5. So okay, so looks correct. Okay, now we are ready to do the homework. Now, so what is the first one? Okay. So okay, basically first y equals to d5. First one is the y, and let's say x is. So let me delete all. I think there must be a more efficient way of the programming, by the way. And then D, no. So x is from 2 to 4, 5, 6. Okay. So there's the x. Good. So for what is the first homework? But actually, instead of let me do everything step by step. Okay. This course page, and let's download the course note. More on regression. Okay, more on regression. So we created dummy variables. Okay. So first, okay, thin R. So I think first homework is simple, just regression, right? So regression 1, which is LM Y. And then, since we don't need a constant, drop -1 and plus x. Okay. So basically, in this regression, I implicitly assume that beta for all three stocks are same, right? But that is usually not true. Okay. Regression 1. Okay, so let's see. So if I see the regression result, then market factor is very significant. Okay, and then value factor is very significant. So value factor is significant and is positively related, and it is less than 1. Okay, less than 1. Okay. And small minus big, it is insignificant. And then our two dummies are actually not significant. Okay, two dummies are not significant, which means that it doesn't add anything. Okay, basically, it doesn't help us to distinguish individual stocks. Basically, okay. I think this is the first regression, and if we wanna add interaction, then we have to expand X. So to add interaction, we have 3, right? So actually, well, as a matter of fact, I think actually we have to add constant in our regression. Do you know why?
Because we only use 2 dummies instead of 3.
Yes, so basically there are 3 forms, right? So if we include constant term, basically we have to use 3 dummies. But since we include constant term, so it means we can use only 2 dummies. So therefore, we have to include constant term, and let me see whether constant term is significant or not. Okay, still constant term is not significant, so there is no like industry effect. There's no firm specific effect in this regression. Okay. And then next, let's add interaction term. So there is only one interaction term here, which is PG dummy and GS, interaction of PG dummy and GS dummy. Okay. What? Okay. I'm slightly confused. Actually, basically, we cannot define interaction effect in this homework. So actually, my homework was wrong. We cannot define interaction effect. Do you know why? You know, in our class note, we have a dummy for white and dummy for like sex, right? Male, female, and dummy for gender, male, female, and dummy for races like white, Asian, black, something like that. And the interaction term means something like white man or black female, something like that, right? But in our homework, basically, we cannot define that kind of interaction. You know what?
Because stock can be...
Right. It is impossible. There is no stock which is included in both sectors simultaneously. So basically, we cannot define interaction effect. I'm sorry, I didn't saw it through last class. So I think maybe that's why your program doesn't work, because of because interaction effect. So if we define interaction effect here, then interaction term is all 0, right? And if one of the columns is all 0 in our data matrix, then which means our data matrix doesn't have a full rank. So we cannot define, so x prime x term doesn't have inverse matrix. Okay. Anyway, so this is our homework. So yeah, let's do one by one. So first, likelihood ratio test. Okay. So first, let's assume that consider null hypothesis such that all dummies are simultaneously zero. Okay. So basically, we explicitly, okay, already tested whether individual dummies are significantly different from zero or not, which we can know by looking at the p-value or p-value of those two dummies. So since p-value of those two dummies are like 60% and 90% almost, which means that we cannot reject null hypothesis that these two P&G dummy and Goldman Sachs dummy are zero. Okay, so we cannot reject that null hypothesis. But actually, we didn't test whether these two dummies are both of them are zero or not. Right? Individually, we tested it. They are not statistically different from zero. They are not statistically different from zero. But we don't know whether both of them are together jointly, whether statistically different from zero. Right? And of course, our case is that this p-value is so high in both cases. Therefore, the joint hypothesis that both of the interaction effects are, both of the dummies are not significantly zero, we think they are likely to be true, but anyway, we want to test it. Okay? So how to do that? So first, basically, we want to get the residual for restricted regression and unrestricted regression. Okay? So regression error from restricted regression is under the restriction that those coefficient for those two domains are jointly zero. Okay. For unrestricted regression, we didn't impose that one. Okay. So first, let me calculate this one. So I think there is easier way and a more interactive way. So rank one. Okay. So if we do and residuals. Okay, then basically we can get the residuals. Okay, which is error term from the unrestricted regression. Okay, so the summary over here. So first, okay, so we need to system RSSR, actually RSSU. So basically RSSU is basically, okay, one of the residuals, okay, and then next we need a residual, okay, and then sum of the squares. Okay, how can I do the sum of the square? Square sum. Let me just open. RSSU. Oh. Okay, so okay, something like this, and then sum. Okay, good. Okay, so basically what I have to do is then I have to square it and I have to add. Then it is residual sum of the squares, okay, from unrestricted regression, okay, and then we need restricted. So let me change the name. So regression of unrestricted, and then okay, U, okay, and next we need regression from restriction, where R. So if we impose restriction, basically we drop two dummies. So basically our regression is LM, okay, Y, and then instead of X we have actually X, and then 1, 2, 3. Okay. So basically in the so this is unrestricted regression, and second one is the restricted regression because I impose coefficient 0 to the dummies, right? Ratio, okay. So RSSR should be something like this, okay. Okay. So everyone follows, right? Everyone can follow until this point. Any question until now? No question. So basically, I just constructed this one and this one, okay. And since I constructed this one and this one, next I have to compute well, basically I have to construct F statistics. Okay. In the F statistic, so F statistic is F1. Okay, let's call this one as F1. Should be okay, RSSR minus RSSU divided by K. Okay. RSSR minus RSSU divided by K. Oh, I have to define K. So what is the K here? What should be the K?
Number of dummy variables.
That is true in this case, but K is actually number of restriction, right? And in our case, we impose coefficient for every dummy is 0. So basically K equal to, which is coincidentally equals number of dummies in our case. Okay? So K, okay. K, let's say 2, which is number of restriction. Okay. Okay. And then okay. It's not T. Okay. N1 T. So okay. Notation is slightly confusing in this case. So okay. Okay. So T. So okay. Divide this one with. Okay, first I have to divide with RSSU. Okay, now minus. Okay, actually not minus. Okay, RSSU and divide it with. There's too many. F1 nominator, okay. F1 denominator is RSSU divided by RSSU divided by okay. What? So instead of T, what should we put here? It should be N, right? So T is the number of observations. So in our case, number of observations is basically N. Okay. Big N. So instead of small n, which number should we use? What is the small n? What does this small n mean? Yeah, number of eggs. Okay. So what should be the small n here? Okay. What it should be?
5.
5?
No, it's
Actually, I think it is 5 is right. The,
2 to 6.
the n is actually not 5. N should be 3. Okay. N should be 3, and we have constant, so we add a 1. Okay, 1, and then k. Okay, we put k. K. Okay, so f1, which is basically ratio of f1 nominator and f1 denominator. Okay. Well, let me see what we have. So source. No such file in the directory. We are okay, so f value is like 0.12, which is very small. So I think we cannot reject the null hypothesis. But anyway, let's take a look at the p-value, okay, of this f statistic. So how can I see the p-value for f statistic? I forgot. Okay, what was it? Do you remember? How can I see the p-value for f statistic? Okay.
I think it's PF.
PF, okay. I mean PF.
PF.
Okay, PF Q degree of the freedom 1, degree of freedom second 1. Okay. Okay. So let's see. Okay. F1 of P value should be PF and F1. And then what is the first one is K. Okay, second degree of freedom is, okay, degree of freedom for second one is, okay, so because it is F distribution was, right, first one is the degree of the freedom of this part, and second one is degree of freedom of this part, okay, so this should be the P value. Let's see. So P value is around 11. So 11%. So what is our conclusion?
This is insignificant in alpha is 0.05.
So what does it mean? So P value is 11%. So what does that mean?
We cannot reject
Yes, we cannot reject what?
no axis in the significance level of 10%.
Dummy variable is not significant.
So what was our null hypothesis? Our null hypothesis was that coefficient for all dummy variables are 0, right? And since p-value is high, 11%, so basically we cannot reject the null hypothesis at any reasonable confidence interval like 1% or 5%. So basically this is the homework. So basically I use slightly shortcut for this part, but I think it is more educational to define this P matrix. Okay, so let's define the P matrix. So basically P matrix over here, okay, is so to define the P matrix, I have to add constant term. Okay, so so let's define Z. Z is basically C bind and X and then 1 and X, right? In this way, I created one vector in front of this one, right? Because in this regression, we have to add constant term, right? So I included just constant term, right? This is Z. So Z is our new kind of data matrix, including constant. Okay. So first, I need projection matrix of the restricted one, restricted regression. Okay. So in this case, so okay, so Z1 is X 3, so without dummy variables. Okay. And Z2 is unrestricted. Okay. Okay. So I don't need this part. Okay. So Z2. Right. So next I have to define projection matrix. So basically P, what does it call? P, what is the P? It is px. Okay, px in this one is pxz. Okay, so instead of this, I simply will call this one p1, which is basically px. Okay, and p2 is basically pzx, xz, xz. Okay, so in order to define this, x prime, okay, so t this following, okay, x prime x inverse, okay, inverse, and then c1 t. Right? As you remember, projection matrix is X. Right? This is the projection matrix, okay? Projection matrix PX. So basically, if we multiply any vector over here, it means we are getting the projection image of y on the plane spanned by x. And then second, I need a projection matrix pxz. So instead of I copy this one and then paste. And it's the one I add 2 everywhere.
PXZ simply means in the unrestricted
Yes.
part.
Yes.
I
So
thought
it is a projection matrix on both x and z. Okay. So in this case, right, we have in class note, okay, we have this X part and Z part, right? So unrestricted regression is basically projection on both, actually projection on the plane spanned by both X and Z. Okay, and restricted regression means projection on the plane spanned only with X. Okay. So there's a projection matrix. Okay. Therefore, this is projection matrix, and then I have to define. So since we are getting the error term, so we have to projection on the space orthogonal to either X or X1 and X and Z, right? And I have to now define projection on the orthogonal space, which is M1 and M2. Let's M1 is basically let's check the data first. Okay. Okay. How can I get identity matrix?
Oh, it's a DIH. IH.
This one?
H. DIH.
Oh, okay. Good. Okay. So basically, diagonal DIAG n minus P1 is projection on the orthogonal to X. Okay, and M2 is the projection. Okay, which is a projection orthogonal to the space spanned by both X and Z. Okay. Now, the regression error is basically projection on the orthogonal space, right? So basically, E1 is, what is Y? Okay, we define E1 is basically M1 multiplied by Y. Okay. E2 is basically M2. Okay. Y. Get it? Now, of course, RSS1 is basically E1 sum. Okay. RSS2, which is unrestricted, is sum E2. Okay. Right.
Isn't it trace of the E1?
What do you mean by?
I think there's like apostrophe in the RSS.
Oh yes, that is true, but basically they are same in this case. Actually, they are not same. So if we do in the R, okay, in R, okay, basically we want to calculate this, right? But so in R, to implement this, of course, we have to do this. Right? This is the right one, but basically this is the square of the individual element and summing it all, right? So basically this is simply, right? And then E is basically square of individual element, right? And then by getting the sum of it, we are getting this one. Okay, so E1, E2가 없습니다. Okay. M1, M2가 없습니다. Okay, so basically if my method is right, RSS1 should be equal to RSSR. RSS2 should be equal to RSSU. Okay? So let me see. Okay, see? RSS1, RSS2, RSS and U, and RSS. So So yes, I think this one is the same to this one, and this one is the same to this one. So any question? So basically now let's implement this formula alternative way. So basically F1 F2, okay, F2 equals, so basically first element is basically RSSR minus RSSU, okay, so this one is denominator, so RSSR minus RSSU should be equal to actually this one, okay, this one, so TY and then basically P and then P unrestricted projection minus restricted projection, okay. So in our case, what is unrestricted projection? So P2, okay, P2 minus P1. Wow. Okay. And F is denominator. So denominator is this one. So RSSU minus divided by this one. Okay. So RSSU is, let me change the order. So RSSU is RSS2, okay, divided by T minus what is N? N is 3 plus 1 plus 2. K divided by K.
N minus.
Which is N. Actually, okay, so F2 will be equal to F2 1 divided by F2 2. So let me compare this F2 with F1. Okay, they are, oops. What is going on? They are different. Okay, so this and these are the same, which means sorry, I have to divide it with K. Okay. F2 divided by K, then 1, 2, 5, 6, 1, 2, 5, 6. Okay, so they are the same. So this is our F test. So we did F test, actually likelihood ratio test in 2 ways. So any question until now? No. So which part do you think you made a mistake? Sway?
I tried to configure the projection matrix.
Okay, project.
Yeah, PZ, but I thought that it was project matrix of x multiplied by z. The matrix.
Okay. Okay. So how about you? Where do you? I see. So same. Okay. So anyway, yeah, it is not multiple. It is simply projection on the space X and Z. Okay. So this is the likelihood ratio test. And next homework is okay. And next one is basically word test, right? And word test is what is the restriction? Okay. So let's go to the homework. And then conduct wild test about sum of the coefficient for sector is 0. So next our assumption is whether okay. This is our assumption. Actually, I think we can impose more interesting assumption like this. So coefficient for P and G, and then coefficient for GS are same. Let's assume. Let's test null hypothesis. This one. And so, given your intuition, if it is our null hypothesis, if this is null hypothesis, and if we do the word test, then do you think we will reject or accept? Cannot reject this hypothesis. What is your thought? Do you think we will gonna reject, or we will not be able to reject? 현정, what is your view? Yes, okay. 병철, what is your thought? Different, okay? So it means we can reject null hypothesis. We reject null hypothesis. Actually, I think my guess is we cannot reject null hypothesis because in our first regression, the coefficient for both domains are not statistically different from 0, right? Therefore, if they both of them are not significantly different from 0, then both of them are like 0, and it is likely that they are anyway same. Okay, but maybe not. Maybe I'm wrong. So basically, we have to test it. So to test this one, okay, we need to transform P. What this is identical hypothesis. Okay. So to match the notation, so what is the C? So C is 1 and -1. So let's use vector notation. Okay. So now let's do word test. So let's define C is okay 1 and -1. Okay. It is matrix. Anyway, okay. This 1 -1, and then blah blah blah. So basically, we have to construct. Okay, basically we have to construct statistic where. More general word test. Okay, like this. Okay, so let's use this one. Okay, and then since we have only one restriction, so K should be 1, right? So C is like this. So first we have to calculate this. So B is the 0, right? B is 0. Let's write down B equals 0, 0. And in our regression, okay, summary of the, we already did the regression, which is where is it? Regression. Okay, regression from unrestricted regression like this. Okay. coefficient. So we need this one and this one. So 1, 2, 3, 4, 5, 6. Okay, so 5 to 6 in the first one. Okay, so they are the two coefficients I'm interested in. So basically, beta is like this. And then I have to construct first this part, C prime x bar minus b equals 0. Okay, so let's call this one CB. Okay, CB. Okay. CB equals to C multiple C and beta. Okay. Okay. So C C beta. Okay. C yes. So CB beta minus B. Okay, so this is the this part. Okay, but actually this is the constant. So conveniently CB is just constant, and I have to construct this part. Actually, to match the notation, okay, let me use C, which is actually, okay, C and coefficient for everything. Okay. Okay, so basically I put 0 for other coefficient. Okay. And then we have I define okay, Z2 is X in class note Z2, so basically I have to calculate G2. Okay. T C2 C2 of inverse code, and then I have to multiply C first and next. Okay. C wait to find. Okay. Okay. So this is this part, and I have to calculate S square. And then S2 multiply S2, and I have to do solve again. Inverse of this entire thing again. Okay. And I have to calculate S2. So S2 is okay. S2 is basically regression error. Okay. I forgot. So residual standard error. I don't know how I can get it, but SD standard error. No. SD? No. RSD. Residual standard error. No. Okay. Then I will simply calculate this one. So in order to calculate S2 which is equal to, where is the RSSU? Okay, I calculate residual from unrestricted regression already, and divide this one. Okay, with actually I can deal with this one. Divide by n minus 6. Which is basically the same to this one. You 6, 9, 6. Okay, they are same. Okay. 2 is this one. So we are almost done. So we have this part. So I have to pre-multiply this and this. Pre-multiply CB. Okay. This is world status 1. Okay. Of course, I have to divide this one with k, but actually k is just 1 with 1 restriction, so I think this is fine. Okay. So to run the program, dummy, and if we get W1 looks like this, about 0.12. So it is very low. Okay, but anyway, let's check it. But is F distribution with the same? So where is the F? Okay, P value. W1 and W1 P value, and degree of freedom. First one is K. Okay, but K is actually 1 in our case. And second one is t minus n plus 1. Okay, t minus, so we have actually so since k is already 2, so this is fine. Okay, so p value is therefore, so p value is like 30%. Okay. So what is our conclusion?
We cannot reject the null.
So we cannot reject the null hypothesis. What does that mean? So basically the coefficients are basically the same. Okay. More rigorously speaking, we cannot say they are different. Okay. We cannot say they are not same. So we finished the world test, and they are very, very important. Okay. Any question until now? Any other homework? So X test, okay, word test, okay.
How the likelihood test and the wall test different from each other?
They are, well, as you can see, they are very different. But eventually they test the same thing. They test the same. It is the two-way. Basically, there are another way, but they are two different ways
different
to
way to
test the hypothesis. Any other questions? So actually, we can, you know what? We can test this one. So basically, we test this one with word test, but actually, we can test this hypothesis with likelihood ratio test as well. Do you know any idea of how we can do that? Right? In the likelihood ratio test, basically, what we learn basically there are variations of likelihood ratio test, but basically we test whether all coefficients are jointly zero or not. Okay, and how do you think we can transform this problem slightly so that we can test this hypothesis with likelihood ratio test instead of word test? Any idea? Actually, we don't even have to use likelihood ratio test. I think we can even test this one with ordinary, just OLS regression. Do you know how we can do that? For this type of hypothesis, we don't even have to use this one. Okay? We can simply run the regression, and by looking at t-value, we can test this hypothesis. But to do that, we slightly have to change the data. So, basically, okay. So, suppose this is our regression. So, error, okay, and we want to test whether. We want to test this one. Okay. Then one current way is what I will do. Okay. In this case, is basically I will do. If they are same, okay. If they are same, and to some alpha. Oh, actually, I think we can use likelihood ratio test. So basically, we can transform problem like this, okay? If they are same, okay. So basically, what we can do is we can run two regression. So this is basically restricted regression, okay? Okay, and this is basically unrestricted regression, right? So in this case, if this hypothesis is really right, even if we run regression in this way, okay, it shouldn't matter, right? basically whether we run regression this way or this way, it shouldn't matter in some sense. Right? Because anyway, the coefficients are same. It shouldn't matter. So what we can do is basically we run regression from this and to get the residuals. We run regression from this and get the residual. So it is unrestricted residual and then restricted residual. And then basically we can compare the two residuals. So residuals, and basically we can do this one, okay? This F test. Then basically we are basically doing the thing. Anyway, do this exercise yourself at home if you have time. I think you should work.
The residuals follows F distribution.
Residuals don't follow F distribution, okay? Ratio, if our hypothesis is right, this ratio of the residuals in this case should follow. Okay, not with the ratio. So in sum of the squares of residual sum of squares and difference of residual sum of squares, the ratio of basically anyway, not residual itself. Some of the square and differences and those things, this ratio should follow that. Any other question? Basically, in this case, basically, actually, right. Okay. Any other question? Okay, let's take 15-minute break and resume the class. Somehow, so it is correct model. So ideally, we have to include both X and Z for our regression. Okay? But somehow we drop this one and run the regression only with X, okay? And we wonder what's going to happen. Okay? So i.e., she does not include the Z variable. Then what are the properties of the beta hat? So what are the properties of the coefficient of the regression with omitted variable? Okay? So as we know, the beta hat basically looks like this. And then instead of y, okay, since this is the correct model, okay, so we put this into here. And then, okay, so it's the y, we put x beta z gamma plus, which is the correct specification. And then if we do the computation, then this cancels out, so we have only beta. And we have this part z, and we have this part about the L. Okay. And therefore, even if this term is 0, which is basically our assumption, right? In our usual OLS assumption, of course, X and U are independent. We assume they are uncorrelated, right? Uncorrelated. So basically this is 0. But even if they are 0, okay, since because of this term, okay, our estimate of the beta is different from true beta. Right? So it means if we omit the variable, so if our model, our empirical model drops some important explanatory variable, then our estimated OL coefficient is biased. Okay, biased means the expectation of our estimated coefficient is different from the true beta. Okay. In our previous case, so anyway, so this will be different from beta unless either x prime z is 0 or gamma is 0. Okay. So actually this is an interesting case, right? If gamma is 0, it means by definition z is not important variable, right? So it doesn't matter whether we draw or not. So if gamma is 0, it is fine. But this is more interesting case. X prime z is 0. Okay. So about this part, okay, this part is called bias. So this because of this term, okay, we have bias. Okay. So what these two special cases correspond to? So these two special cases is this case and this case. And this case is obvious. Okay. What about this case? What about this case? What this? So basically x prime z is 0. So and economically speaking and intuitively speaking, what does that mean? Okay. When do you think we will have x prime z would be 0? So I mean, geometrically we call this case as orthogonal. If x and z are orthogonal to each other, okay, then it means even if we drop the variable z, still we can get a unbiased estimator. Okay. So orthogonal means independence is kind of orthogonal. Okay, uncorrelated variable. If x and z are uncorrelated, it's kind of orthogonal case. Okay. But anyway, I think it can be better understood with an example. So consider an example of a wage equation with omitted measure of the ability. So suppose we wanna estimate wage. So there is a wage equation. So in our example, okay. So this is wage equation. So this is our wage equation. But I mean, intuitively speaking, okay, the wage should be increasing function of ability, right? People with higher ability should receive higher salary, right? So ability, we know ability will affect age, right? Wage, all the people, and clearly in this relation we don't have ability, right? So if we don't have ability, okay, then what's going to happen to those variables? What's going to happen? Do you think going to happen to do this coefficient? They are clearly biased, right? I mean, first, do you think this coefficient will be biased or not? So since we don't have ability variable in this regression, what's going to happen to those coefficients? Any guess? Actually, first about beta one. Okay, beta one. About education. Education. Okay, what's going to happen? In comparison to true beta one, which will include another independent variable about ability over here. Okay, then we will have a true beta one. But since we don't have a true model, we don't have variable for ability. Okay, and if we simply run this regression, how this beta one will be different from the true beta one? Again, 병철, what is your guess? It will be overestimated. So, in comparison to the case with ability, do you think the estimated beta 1 is greater than true beta 1 or smaller than true beta 1? Beg your pardon?
I think it will be higher.
Why?
Because without the in the equation, without the other significant variables like ability. Well, in the without the ability, people tend to value greater in the education.
No, I mean It is not related with people's choice. It is simply about data problem. So suppose we don't have ability data, right? Actually, ability data is very difficult to get, obtain. Right? I mean, it is even puzzling how to measure ability, right? So I mean, the question is, okay, whether this term is positive or negative, right? If this term is positive, do we overestimate or underestimate the coefficient? Suppose this whole term is positive, then do we overestimate or underestimate the impact of the education? Okay. If this whole term is positive, okay, then do we overestimate the effect of the education or underestimate it? So anyway, suppose this whole term is positive. This term is positive, then clearly our estimated coefficient is greater than the true coefficient, right? Which means our coefficient will overestimate the coefficient, right? Which means overestimate the impact of education in the previous case. If this whole term is negative, then basically we are underestimating the impact of education, right? So the question is whether this whole term is positive or negative. And this term is positive semi-definite, so this term is not important. So only this term matters. Whether, so this, where in this case, X is education and Z is ability. So our question is whether X prime Z is positive or negative. So if interaction of education and ability is positive, right? Positive basically we are overestimate the effect of education on the wage, right? And if ability and education have some negative relationship, okay? If it is negative, then we are basically overestimate the effect of the education, okay? So what would be the case? Do you think the interaction of education and ability should be positive or negative?
Positive.
Right, it should be positive. What's the point of you taking class here, right? Otherwise, you are taking this class because you are like more competent people, right? People with more ability. Additional ability about statistics and economics, right? So it is likely to be there is a positive interaction between education and ability, right? So therefore, this term is greater than 0, which means this term is greater than 0. So without ability, if we run the regression, then it is likely that we are overestimating the effect of the education, right? And that is actually intuitive, right? And if we drop the ability, if we don't get the data about ability, and simply we run the regression on the education, which means that some effect of the ability will be included in the education, right? So education will pick up some part of the explanatory power of the ability, right? It should be, right? Because education and ability are correlated. Therefore, if we drop the ability and only use education, then basically we are overestimating the effect of education. Okay? How about others? Okay, how about others? How about age? So age and ability, it is hard to tell, right? So I think in this case, the interaction with age and ability would be close to 0. I don't know, maybe. I think maybe there's a non-linear relationship, right? With age and ability, right? So as we get older, we will have more and more ability, but we are too old, then our ability will be dropped, right? So clearly there will be a relationship, but it is not straightforward. Okay. So in this case, suppose beta 1 Okay, so suppose we find beta 1 is positively significant, right? In this relation, suppose we find beta 1 is positive and statistically significant, but then we have to suspect our result. Our result so maybe since we drop ability, and since if we include ability, maybe because it overestimate better. So if we include ability, maybe it can turn out to be insignificant, right? And about those other variables, maybe since they are not that related with ability itself, maybe overall, maybe people with ability will live in the city, okay. But for others, maybe they are not that related. Then in that case, we can maybe believe the question for this and this and this. Okay, maybe be able to believe them. What's gonna happen if somehow we are living in a very weird world, and somehow we run the regression and we find this beta 1 is negative and significant. So it means if we get more and more education, somehow our wage decline. Suppose we found this relationship and we don't have ability, then how can we interpret that coefficient? Okay. Do you think we can believe it or not? Suppose this one is significant and negative. We can believe, but we don't have ability. In that case, do you think we can believe that education negatively affects wage? In this case, 현정, what is your thought? Why?
Education is something I need more data about education.
Suppose you have all the data about education, okay, and you don't have data about ability, then what's going to happen? And you find that this is one is significant and negative. Then what will be your reaction?
I don't have data about ability and
Yeah.
I have data about education and the education negatively affect the wage, then I believe education is negatively affected.
Why? Yeah, that's true. So why? Jay, why?
Maybe I don't have enough data about that.
No, that's not the point. Even though you don't have data about ability, in this case, you can still believe it. Okay? Again, without ability, and we know ability and education are kind of positively correlated, and we find it's a significant negative. And we know this overestimate the effect of education, right? So this minus should be even further minus, okay, in some sense, right? So already it is significantly negative. So if we include ability, then it should be even bigger minus, right? So therefore we can believe this one. In this case, we can believe education will lower our wage. Okay. Any question? Next one is asymptotics. So again, consider the model y equal x beta plus epsilon, and then again we have OLS x beta, which is x prime x inverse x prime y, and instead of y we plug x beta plus epsilon, so we have this equation. Okay. Now, okay, until now we didn't assume anything about distribution of this epsilon thing, right? But if we assume that epsilon is distributed with norm, such the mean 0, and sigma square. Then beta hat is a linear combination of normal random variable, and it itself is a normal, right? Because this is constant, this is all normal, and this is all constant. This is a linear combination of normal variable. So as this is normal, so this should be normal, right? Linear combination of normal variables should be normal. Therefore, beta should be normal, right? We already know beta hat is unbiased estimator and variance covariance matrix like this. But suppose we don't want to assume this, okay? Suppose we don't want to assume that epsilon is distributed in normal. In that case, what can we say only? That beta hat would have a mean beta and have standard deviation. Okay, various covariance matrix of this one, but we are not sure whether. But we don't assume anything. We don't know about anything about distribution of this thing. Okay, this is beta. But the point of this asymptotic means that if the point of this section is that if we have enough data, okay, if we have enough data, basically, even if we don't assume anything about this beta, basically, it will converge to normal distribution. Okay. I will show why. Okay. However, if we focus on the fact that T is large, which is observation, we can make much more headway by using asymptotic distribution as an approximation. Okay. So returning to equation, previous equation, so we know this equation, and suppose we divide this one by T, but we have inverse, so which means we have divided by 2. Okay, right? Basically this cancels out. Then the law of large number. What is law of large number? Do you remember? Okay. By the law of large number, this one converges to 0 as t becomes infinity because this one is 0. Okay. Why? Okay. What is law of large number? Do you remember?
If we select a large number of samples, the statistics of these samples will eventually be same as the statistics of the population.
No, there is called the central limit theorem, I think. Okay. Law of large number is basically sample mean will converge to true mean. Actually, I think so. Okay. It's only confusing. So let me check law of large number. Law of large. So LLN, okay, law of large numbers. In law of large numbers, it is a theorem that describes the result of performing the same experiment of large numbers according to law of the average. The average of the result of the large number should be expected to know. Okay. The average sample mean will converge to true mean if we have a large data. So what you just said is called the central limit theorem. Central limit theorem is very similar to this one. Okay. Actually, we can derive law of large numbers from central limit theorem. Actually, so you are not entirely wrong. So central limit theorem states under which the mean of a sufficiently large number of independent random variables with mean and variance will be approximately normally distributed. Okay. Approximately normally distributed, which is central limit theorem. So if we have a large number of data, then actually we convert to normally distributed, and then variance will become 0, close to 0. So basically, if we have a large number of data, it will convert to normal large number because the variance will become 0 and it becomes a constant. So anyway, law of large numbers, because sample mean will convert to true mean, and we assume that true mean is 0. Okay, so this one should convert to 0. Okay, and suppose we assume x prime x divided p system will convert to some matrix W. Okay, no constant, some matrix where W is a symmetric, positively definite, and finite metric. Then basically this one comes some constant and this comes to 0. So basically if we have a large number of data, okay, then beta hat will become the true beta. Now more formally, actually, we express that the probability limit of beta hat becomes beta if we only have beta hat equals beta st equals infinity, and actually which means that probability limit of beta hat equals beta means that if t is very large, the difference between these will be actually whatever constant, whatever number we have, the difference of this one will be smaller than this with probability 1. So in probability they will getting closer and closer. So I mean, if we have a large number of data, they are very close to each other with probability 1. That's the definition of the probability limit. Anyway, if probability limit beta hat equals beta, then we say that beta hat is consistent estimator of the beta. Okay? And therefore, OLS estimator is the consistent estimate, is actually one of the consistent estimator of the beta. Because we have large number of data, we know our beta will converge to true beta with probability 1. Okay? Therefore, our beta, OLS beta is a consistent estimate. So how consistent estimator is different from unbiased estimator? Okay. How it is different from biased or unbiased estimator? What is the definition of unbiased estimator, 현정? So our OLS beta is unbiased estimator, right? So what does that mean?
The coordinate beta from the true world.
No. So when we say OLS beta is unbiased estimator of the true beta, what does that mean?
It means it is. It can calculate the true.
So okay, you shouldn't confuse this. This means unbiased estimate, right? Our estimate is expectation of our estimation is true beta, right? Which is unbiased, and then this one is consistency. Okay, so in this case, it doesn't matter how many data we have. Right? Even so, in this case, what we are just saying that our estimate is in expectation, same to true beta. Okay. And in this case, maybe it doesn't say anything about expectation of this, but we are saying that if we have a large number of data, then our beta will be converging to true beta. So they are two different concepts. Okay, I have one question. So, do you think it is possible that some statistic, which is some estimate for the beta, is unbiased estimated, but still not consistent? Do you think that is possible? So okay, biased, unbiased. And then we have consistent, so inconsistent. Okay. So in our OLS regression is consistent and unbiased, right? Here. And do you think there is any? Can you come up with any example of this case? Okay, so this case is too obvious. So maybe these two cases are interesting cases. Okay. So do you think there is a possible consistent and biased estimator? Okay. How do you think? Do you think there is a possibility? Do you think it is possible that some statistic can be both biased and consistent?
I think I don't know exactly, but the variant unbiased, biased variance can be example of this case. Because unbiased variance
Yes.
is
Yes. So, Carol, yes.
the denominator, nominator.
Right. So it is unbiased estimator of this one, right? So sigma square, right? So we are assuming epsilon is actually square, right? Square. And k is actually it should be minus. K is basically number of the variable, so it's basically including constant, okay, including constant. Okay. So in this case, clearly this is unbiased estimator. But actually, people tend to use this one as well. This one as well. Okay. Then it is biased estimator of the value, but still it is consistent, right? If we have a large number of n, still it will converge to this. Okay. Just such a small number, k, it doesn't change anything about consistency. So this is the actually biased but consistent estimator. Okay, and actually we have another concept called efficiency. Okay, efficiency of the statistic, and to compare this and this, okay, to compare this and then. So if we compare this and this, okay, clearly this is unbiased and consistent estimator, and this is a biased and consistent estimator. But somehow some people actually prefer this one, okay, because there is a result that this is more efficient estimator than this one. Okay, so to compare this and this one is biased, consistent, but less efficient than this one. This one is biased, consistent, but more efficient than this one. Okay, so we have this. Actually, more parsimonious example would be this beta hat plus 1 over n. Okay? And suppose this is with OLS estimator. Then clearly this is a biased estimator, right? This is because expectation of this one is beta plus 1 over n, right? This is biased estimator, but still it is consistent estimator. And because this term will converge to 0 in probability. How about others? Okay, unbiased estimator but inconsistent. Can you imagine any case which is unbiased? And which is actually unbiased but still inconsistent. Using it is possible. So suppose to the OMS estimator, suppose we add some random variable z. So z is -1 for head, +1 with tail. So if we draw the coin, okay, we toss the coin. If we have head, then z is -1 and t is +1. Okay. In this case, this one is unbiased estimator. Right? In expectation, z is 0. Right? Unbiased estimate, but it is not consistent. Okay. Even if we don't have a lot of data, this one doesn't go up. Okay, so that's the concept of consistency. So in film, beta head is better than we say beta head is consistent to X well beta. Property of probability limit is the probability limit of some function. Actually, we can send the probability limit inside of the function. Okay. Probability limit of g theta head is equal to g probability limit of theta head. Okay. Of course, if probability limit of theta head exists, then of course we need some regularity condition on g. For most of the interesting cases, actually, this technical condition satisfies and probability will exist. Now consider some special cases. Okay, actually let's go directly to this. So beta head minus beta would be look like this from the previous one. And suppose we multiply. Now we wanna multiply square root of the t on each side of this. Okay. Then we have, because this and this cancels out, we have square root of the t here. Then, okay. Then if we multiply this one like 2 times in some sense, so this one multiplied by transpose of this one, then in this case we have root t both times, so we have t and beta head minus beta and beta head minus beta prime. Okay. And simply we plot the definition of this, so it means this term, okay, will look like this term. Okay. So this whole term comes here, and because we have transpose, so we flip and multiply here. Okay. So we have this one, and then we have root t 2 times, so we put this one together with t. Okay. And we know we can send the probability limit inside of the function. So with probability limit here, separately. Okay. So we wanna get the probability limit of this one, get the probability limit of this one, and get the probability limit of this one. Okay. And then about this part, actually we can write this part like this. Okay. Take a little small. Actually, I need to explain more about this part, and I think I will explain this later on. But by now, please, you can just memorize this from here to here. You can just accept the result from here to here. Okay. And then, since this is constant, this identity matrix, so we can put this one here, right? Then this entire thing, this one and this one cancels out, so we have only this one. So sigma square probability limit of this one. And therefore, now we have central limit theorem, okay? By the central limit theorem, this one, okay, this thing should converge to this one, and then the variance of this, variance of this one should be like this one. This is called central limit theorem. Therefore, okay, so why do we need to multiply by? because we want to apply central limit theorem. Thus, there are two ways we can talk about distribution of beta hat, basically. So, I mean, the point is that until now we didn't assume anything about distribution of the beta, right? But if we have a large number of data, basically based on central limit theorem, okay, our OLS estimate will follow normal distribution. Okay? So about the as to our OLS estimate, what we can say is that maybe we can, from the beginning, we can assume this one. Maybe we can assume that our regression error, our error term is distributed with normal, from the normal distribution, then problem solved. Okay, we can do any hypothesis testing. But even if we don't have this assumption, what we have just showed is that if we have enough number of data, even without this assumption, we'll have approximately this. Any question? Oh, I forgot homework today. I was too busy recently, so I didn't have time to. I spent too much time yesterday because of non-solution. Okay, I have to prepare non-solution for your future generation. So I couldn't come up with any homework. But anyway, do your practice, okay, at home. And we don't have any homework this week. And see you next week.